Hello, everyone. Very excited to be here today. Thank you for being here. So we're going to talk about how to build an advanced visual search engine with self-supervised learning representations and Milvus. So a quick word about ourselves. So my name is Noé. I work as a lead data scientist at Sikara. I've been there since 2020. Work mostly on computer vision, and I'm a big fan of volleyball and tennis.
And I am Antoine, and I work at Sikara too for 6 years now. And I am head of science at Sikara.
So just a quick disclaimer, we are not researchers, so we're going to share some results we got on some projects, some opinions we have, but there is no scientific paper behind it. So we're going to build a visual search engine based on similarity of representations. So it's just a system where you input an image, and it outputs the images that look the most similar from your database. So some examples of where such system could be great is when, for instance, if you want to validate if a person's photo is in your database. So imagine you're a big company who wants to authenticate your employees in front of the building. Or if you're Google Lens and you want to, whenever someone takes a picture of a clothes, you want to match it to the most similar clothes in your database. Or just if you have a huge database of images at your company and you really don't know how to leverage its potential. So you just input an image and it will allow you to retrieve the most similar images. So now Antoine is going to talk to you about how image retrieval works.
Yeah, so image retrieval is the underlying task behind search engines, actually. So it simply consists of retrieving an image in a large image database, provided a query that could be either a text or a keyword or an image. When the query is an image, it's called content-based image retrieval, and that's really what we are going to talk about today. So how do we build such a system? The idea is that we rely on a feature extractor, which is a model which can be a neural network or something else, actually. And what it does is that it extracts from an image a representation, that is a vector, that describes the image. So we use the feature extractor to extract a representation from the query and all the images of the database. So we have a large number of image representation from the database. And the idea is to compute similarity scores between those representations. How do we do that? We have several methods to do that. Very simple one is to use distance, like cosine distance or L1, L2. And once you have a similarity scores between the query image representation and the representation of the image database, you can simply retrieve the most similar image by ranking those scores and showing the image accordingly. So when building such a system, there are two challenges. The first one is to have a good feature extractor, because if the representations are not good, you are not going to be able to do good searches. There was a famous problem in computer vision a few years ago. Some people tried to train a classifier to classify wolves and dogs. And they figured out at some point that even if the performance was quite good, the model was using the snow to classify wolves because there was a bias in the data set. So imagine you have a feature extractor that describes the snow in the representation but not the wolf, and you want to search for wolves in your image database, it will not work. The second challenge you may encounter is that when you have a large number of images in your database, it can be a challenge to build a production-ready system to compute similarities at scale and to serve the results to the end user. So now we are going to talk about the first change and how to build a good image representation, and Noé is going to show you the first step for that.
So yeah, so when starting any project, the first thing you want to do is building a baseline. So we're going to see how to build a baseline for these image representations. So a common thing to do when you're building a model for any task is in computer vision is that you take a model that is pre-trained on a large data set like ImageNet or Open Images, and then you fine-tune it on your custom data. So is that you adapt your model to your custom domain and your custom task. So we're going to see if we can get decent performance without actually fine-tuning on our custom data and taking just an off-the-shelf model to get a baseline. So to do that, we're going to check if we can classify images doing content-based image retrieval. Images which are very far apart from the training distribution, so from the distribution of ImageNet, so microscopic bacterial images which are not seen in ImageNet. So why doing so? It's actually a real use case we faced. So we are actually still working for a company called Bioreca. And it's a startup that wants to classify picture of bacterial images. And there is actually a high complexity in the data, even within the same class, because there could be different type of microscopes, different zooms, different reactants, which are used to extract the bacteria. And they had no data to start with. And since it's a startup, they want to move fast, so collecting and labeling a large data sets is not really feasible. So we are wondering if we could use content-based image retrieval, so with a pre-trained model. And to confirm our ID, we used a data set called DBAS, which contains 33 classes of bacteria and 20 images per class. And it has a quite low complexity because it's only one type of zoom, one type of microscope. Images from the same class, they use the same reactants. So it's really a subset of our full complexity. But if we can get something working on that, we can deduce that a model pre-trained on one of these large data sets will be able to extract the required features from bacterial images. Someone actually trained a model for this task. They used the MobileNet V2, which is a quite small model, since there are very few data. You can't really use a big model to train it on big model. So they pre-trained it on ImageNet, and then fine-tuned, so they trained the classification layer with 10 images per class, and evaluated themselves on the 10 remaining images, which led to a performance of 95%, which is quite good, because the task is quite easy. And then in our experiments, we performed content-based image retrieval, so basically just use a model trained on ImageNet, compute image representations, and match these representations. So at training, our model has never seen any bacterial images. And what we see is that when we use a MobileNet V2, we get a result of 80%. And we can get this performance up to 84% when we use better backbones. But it's still far from the 95%, but also it's very far away from random. So what we can see here is that it really manages to extract some interesting features to give an interesting performance. So a good way to check why this model is actually working is to visualize the projection in a TensorBoard. So I'm going to check it now. And so each representation has a size 1408, and you just project it in a 3D space doing dimensionality reduction. So it's PCA, but T-SNE works much better. So I'm just going to stop it after a few iterations. So T-SNE is just trying to clusterize the images that look similar. And you can really see there are a cluster of images. So I can color them with their class. And basically, images of the same class have the same color. And if they are close to each other, it means that in the feature space, the model represents them close from each other. So like our content-based image retrieval system will manage to classify them well. So it works quite well, like the different colors are really clusterized. You can see that sometimes some colors are very close to each other. And if we click on this example, so this is one of the cluster, this is the other cluster, and you can see that the image looks very similar. Even for a human eye, it's hard to differentiate them. Since the model wasn't trained on that, it's quite easy to understand why it's making some mistakes. So how to create such projection? It's a bit harder with TensorFlow, but much easier with PyTorch. So you just use the summary writer from the TensorBoard plugin, create it, and then call the add embedding method with your matrix of embeddings, your images, and some metadata, like the classes, to create it. And then you can launch that, and you get this great representation. You can click on testNIP, PCA, and there are many other things you can explore. So to the question, can we classify microscopic bacteria images using a pre-trained model on ImageNet with no fine-tuning? The answer is yes. So to conclude this first challenge, Antoine is going to talk to you about how we can improve these representations with self-supervised learning and visual transformers.
Thank you, Noé. So the first thing you may ask is why? What does SSL and vision transformer has to do with image retrieval? And this idea come at ICARA when we read this paper like 2 years ago, I think. Yeah? Maybe you've heard of it. It's quite famous. It's a paper called DINO. And it talks about self-supervised learning and vision transformers. Here is the main table of results from the paper. So there are several methods that are compared, supervised and unsupervised methods, and also different feature extractor. RN50 stands for ResNet 50, so it's a convolutional net, and vision transformers. The last two columns, linear and KNN, describe the method to evaluate the model on ImageNet. Linear, it simply consists of adding a classifying layer on top of the feature extractor and fine-tuning it. And KNN, it's a bit more challenging. It's directly performing a classifying task in the embedding space out of the feature extractor, so in the image representation space. But it's much closer to the image retrieval task, which is interesting for us to build our visual search engines. So if we look at the linear performance, what we can see is that the first line is the supervised baseline, and then you have a list of self-supervised methods. And what you can see is that there are a steady increase in the performance within years. And the DINO line was 2 years ago, so now the performance is even better than that. And what is remarkable about this result is that it achieves that without requiring any labels. So to understand how it does that, we should dive a little bit into the DINO algorithms and see how it learns good representation. So here I choose randomly an image that is going to be seen during the training phase. So the first thing we do is to extract crops, global crops, that is the huge bottom crops, and small crops. And we perform data augmentation on them, like color jitter or flips, classical augmentations. And the idea is that by doing so, we build several views of the same object, a bit like if you were there and you took picture with your phone and moving around the monument. And when you have this different view, we put this image into our feature extractor and we get representations. And the training objective is to make this representation being the same. And by doing so, we force the model to encode visual features that are common between the global crop and the local crops into the representation. For instance, this one, you have a horse. So maybe the model is going to have something in the representation that will encode the horse, which also appear in the global crops. And small crops and big crops are extracted randomly so that in the end you end up with a representation that will describe everything that is visible in the image. And it does that without requiring any label. And something really interesting in the DINO paper, and it was surprising to the authors themselves, is that when you use vision transformer, and only vision transformer, it does not work this way with convnets. The KNN performance came very close to the performance you got when you do fine-tuning. And this is really interesting for us because when we build our search engine, we compute nearest neighbor in the representation space. We do not perform any fine-tuning. So this is very interesting for us. So now he's going back to the bacteria example and show you what SSL and vision transformer does on this problem.
Thank you again. So yeah, so you're getting familiar with this slide. Now we are asking ourselves, can we get even better representations with DINO? So just quickly looking at the results, the two lines at the bottom, you can see that you actually get a better performance than with supervised backbones. It's quite interesting, like the difference is not big, not that we're using 10 images per class to represent each class. When this number is getting lower, so if using just 1 or 2 images to represent each class, the difference gets bigger. Still far away from a model pre-trained, trained actually on this data, which kind of makes sense. An interesting thing is that we are not confirming here that using vision transformer gives a better performance than convnets, but it might be because the task is easy. So now let's just conclude. So the answer is yes again, and let's jump to a task which is a bit harder. Of course, here the distribution is closer from what we see in ImageNet, but it's much harder because there are many more images. So there are 762K index images, so images in the database, and around 100K classes. So if you did a bit of math, around 7 to 8 images per class. Yeah, so there are just too many images, too many classes, and too few images per class to train a classification layer, so you have to perform content-based image retrieval. There is around 1K test images, and these images are collected on Wikipedia, so there are a lot of label errors. So this is what they did on the paper. So they trained model with their data sets, and what they see on the test set is that they get 25% of mean average precision, and when they train it on an other data set which contains landmarks, so same task, just not a data set which is not as good, they get about half of the performance. And in our experiments, again, we are taking an off-the-shelf model, so pre-trained on ImageNet. And what we see here is really that vision transformer with DINO, trained with the DINO method, really gives the best performance as they state in the paper. Note that this performance is about half the performance of when you train it actually on landmark images on this specific task. So now we're going to try to understand why this performance is lower and why vision transformer trained with DINO give better performance than vision transformer trained in a supervised fashion. So just a quick zoom on vision transformer. So this is a video from DINO. And one interesting thing is that vision transformer are based on attention mechanisms, like something you may have heard about called ChatGPT. So since it's based on attention mechanisms, you get an output representation, and you can really check, you can really see where this output representation puts its focus on. So which part of the image it carries its attention on. So if you look at the dog, for instance, the output representation really looks at the entire dog and not at anything else. And on all of these images, it has really a human way of doing where it managed to not pay any attention to what's not important and really look at what seems important in the image, even though we haven't told it to. So if we come back to our model pre-trained on ImageNet, and so the first line are the attention maps of a vision transformer trained on ImageNet in a supervised fashion. And you can see that the attention maps are very noisy. They are very erratic, looking a bit everywhere in the image. And when you look at attention maps with DINO, they really focus on the object of interest, almost like a segmentation map. So even though we haven't told it what's important, it finds it itself. So it's quite, it's one of the reasons why the model trained with the vision transformer trained with DINO gives better representation than the vision transformer trained in a supervised fashion. So if we have a quick look at a dashboard which I spoiled a bit at the beginning, so made with Streamlit, so you can just input an image. So on the left, you see the query image. You will see at the bottom, so the attention maps superposed to this image, and at the bottom, at the very bottom, just the raw attention maps. And on the right, it's the images from the database, so the 762K images, which are the most similar to my query image. So you can see I input a castle. It gave me castles, so it's quite good. Interesting to see that the attention is really carried on the flag. So it outputs images which have flags as well. So yeah, it's quite interesting to see. So attention maps are great for to analyze the performance of your models. Of course, I come from Paris, so I have to show the Eiffel Tower. And what's interesting with it, so it's a bit of a large image, so it takes a bit of time to compute the attention map, sorry. But what's interesting with it is that it's such a famous picture, so of course it will be in the data sets. So we get exact matches for this one. And really, again, the attention map is really segmenting the Eiffel Tower because it's what seems interesting in this image. When I was talking about the fact there were a lot of labeling errors in this data set, this image is actually not labeled Eiffel Tower like the others, but Pont Rouel, which is the bridge just in front. So quite impossible to get it right. We're not in Paris, we are in Berlin, so I have to show the Brandenburg Tor. My German is not on point. But also an interesting result. So again, it didn't see this image during its training. It was trained on ImageNet, so it's just trying to extract the feature of interest. And it's really focusing on the horses pattern at the top with what it finds interesting, and of course, the pillars. So the first images which are found are like images with like pillar-like structure. And very quickly, it managed to find the exact match, so the Brandenburg Tor, because it focuses as well on the horses pattern. So like even though it's a completely different view, it's very cropped, it managed to match them. And now we're going to have a look at kind of the limitation of this method. So it was never trained to match landmarks. So it's just trained to match what seems interesting to it. So if I just input a top view, which will appear in a second, what seems interesting to it, to the model, is the fact that it's a top view and not the fact that it's this specific landmark. So it will just match top views. So it's really one limitation of this approach, which may explain why we get such a lower performance than when we actually train a model on this specific task. Another interesting thing to see is this image. where there is a huge sign in front of the landmark, and you can see that the model is really focusing, the attentions are really focusing on the sign. So it's not at all matching buildings which should look like this one, but really it matches building with signs on them. So it's really one of the limitations of this approach. You don't control what it's going to match. It's just focusing on something that seems interesting. One fun thing you can do is mixing up representations. So for instance, you just take two different images, you put them through the model, you get two image representations, and you just take the average of your two representations and consider that it comes from an image, and to get the most similar image. And so I kind of spoiled the first result I'm going to show. If I just put this picture here and this picture here, the first match that is output is really a mix of the two images. So really a castle with like the water pattern in front. So we manage actually to mix up the images, and then the other matches are completely off. So it could be either that this approach is not working perfectly well, or just that there were no other images in the data sets that looked like both images. And then I can have some fun doing other stuff. So if I put a beach image, can I actually get a castle on the beach? And yeah, kind of. So, and last one, if I remember the image which was focusing on the sign, can I have a sign on the beach? So not in the first one, but in the second one, I managed to get a sign on a beach. So quite fun thing to do, and then you can change the weight you want to carry on the first image, for instance, so to have more weight on the second image, so now it kind of completely forget the first image. But really, now imagination is a limit. Like you can just put 3, 4 images, have different weights, and it could be quite interesting if you are looking for a specific image in a database. Like you're inputting the first image, not quite the one you want, so you're inputting a second image, etc., etc. So far, we are just 2 data scientists in a garage, but now we want to have users and to make it accessible to people. So we're going to try to deploy it.
Yeah, so I am the production guy. And now we have to put this in the hand of the end users that can be many. And another challenge is when the image database increase, because remember, we have to compute representation for all of this image and compare the query with all of them. So if we implement a naive way of doing this, the complexity is actually linear in the number of the image in the database. So we have to find a way to cut the complexity. One solution is an algorithm called the approximate nearest neighbor. So it's an approximation, it's not exact, but it's very fast. And I will not enter the detail, but the idea is that it will compute clusters of all the image representations of the database, and it will do so recursively so that to build the tree in the left part. And when you have a query representation, you simply go down in the tree and you find the nearest neighbor very fast. So if we sum up, we need a tool to first to store the representation. If you have a lot of them, you want to store them in an efficient way. We have to index them. Index means building the tree I showed you before. And not only you need to build the index at once, but you also need to rebuild it when you, for instance, add new images to the database or remove some. And finally, you need to be able to perform search in this database in an efficient way. If you have many users that do simultaneous search. So we identify a solution that is called Milvus. It's a vector database that that tackle really this point. When we were looking for a solution, we consider first Elasticsearch because we used it a lot at Sikara. And it's very good, and it can handle vectors, and it also has approximate nearest neighbor algorithms. But it was not fast enough for our needs. So we switched to Milvus, which is really specialized for vectors, and it is faster. There is also Face. It's a Python library implemented by Meta. It's really focused on the index algorithms. It does not provide a database to serve the predictions. There is also another solution that is called Qdruns, which is written in Rust. And it seems, according to Qdruns, that they are faster than Milvus. We didn't consider this option at the time because it was really a starting project and Milvus was a lot more popular. But right now, maybe we should check Qdruns. And now Noé is going to show you how we deploy Milvus, the different options.
So basically, there are, if you want now to deploy Milvus on your project, there are two different options. The first one is like the easy version. The easy one is a standalone version. So it's simple and it's very ideal for testing. So you just have a Docker compose that comes with Milvus, since it's open source with free services. The first one is Milvus standalone. So it just basically all these microservices packaged in one to make it simple. Then you get one service for the object storage, which will contain all your image representations, and a key value store and etcd, which will basically be the database that allows to handle the main interactions. But when you want to deploy it to productions and to better manage the performance and memory, etc., the cluster version is more adapted, but it's more complex because all these microservices are deployed individually. On top of that, there is also a log broker that comes with it, so Kafka or Pulsar, which allows to receive the different requests from the user and process them accordingly. So, of course, there are tools to help you, like if you're doing Kubernetes, there are hand charts and stuff, but still quite hard to manage. Like, don't do it if you don't have a DevOps team. One great thing about Milvus is that it comes with a web interface called A2, which allows you to manage your different collections. So right now, I have only one, which is my collection, which contains all my image representation of a Google Landmark V2. And it's great to see if everything works and do some testing and some managing. We are in PyData, so I have to show some Python code. So here's just some quick code of how to interact with the Milvus SDK. So it's very similar to Elasticsearch or any database, really, if you worked with some. So you first have to connect to it. Then you create a schema of your different fields, which will be your metadata, and you create your collection. Then you insert your data in a couple of line of codes. And then you call the createIndex method, which will basically run the approximate nearest neighbor to index your data and make them easily searchable. When you have indexed all of that, searching your data is equally simple. So again, you have to connect. Then you have to load the collection. Loading the collection means taking it from disk to CPU to make it searchable. And then you call the search method with your query representation to be able to search it. If we have just one quick last look at the dashboard, you can see that there are these extra lines. So because it was Milvus that was working behind it. So for those of you who arrived early and saw me struggling with the dashboard at the beginning, it's because I forgot to launch the engine. So this is the engine behind it, and it's searching among 762K images. And it managed to find this result in 0.032 seconds, which is quite fast. Also considering it's the standalone version, so it can be even faster. So just quickly, some pros and cons of this solution if you're considering it. The first cons is, as I said, it's quite hard to manage the cluster mode. You need a DevOps team. And we faced some bugs. In the recent version, we are facing some bugs which took us a lot of time, mostly to the DevOps team. And of course, they were fixed, luckily, in more recent versions, which are now stable, but it took some time to follow. So for the pros, it's scalable and fast. It's open source, so it comes with many advantages. There are many features, like partitions. So for instance, if you want to search in a subset of your collection, it's feasible. Hybrid search, etc. I won't go in all the features. There is a web interface, as we saw, a strong community to help you, a good documentation, and a managed version. So if you don't have any DevOps team, I will really recommend just give him some pennies to Milvus so that they deploy it for you, and it makes it much easier. So to conclude, some of the main takeaways of today is that we can build how to do image retrieval with DINO pre-trained on a large data set like ImageNet, to test yourself on data sets which are actually from a distribution which can be quite far away, like DBAS or Google Landmarks V2. And we saw how to deploy it into production. So image retrieval can be great for many tasks. Mainly to start a project, as we saw with Bioreca, could be challenging to get enough data to train a good model, so you could consider doing image retrieval. And SSL is great, so self-supervised learning is great for many things as well. One good thing it could be good for is when you have a project which has been in production for a long time, so you've been just collecting millions of unlabeled images, and you don't really know how to leverage their potential, so you can just train it with self-supervised learning. So yes, but it comes with some defaults that it's quite expensive to train. But
yeah, so what could we do to improve our search engine now? So obviously, we could use LLMs as anybody right now. More seriously, before ChatGPT, there were DALI on multimodal models. Multimodal models could be very helpful to improve the search engine, as they have common representations for text and images. This would allow, for instance, to have more complexity in the queries. You could query the database using a text or an image or both. And this last week, DINO V2 was released. DINO V2 it's very similar to DINO, but they scaled the model and the dataset. So they trained a much larger model. I think it's a billion parameter model, something like that, and they used that to distill a smaller one. So this is really inspired from what is going on LLMs right now. And it's really recent, so we didn't try it yet, but it's similar to DINO, but with much better image representations. So we can simply reuse all what we show you today and plug DINO V2 instead of DINO. So thank you very much.
Yes, thanks a lot. That was a great talk. I learned a lot of things, and I think all the people here learned a lot of things too. We have a lot of questions, so let's do some questions. Do you have any insight on how do the self-supervised DINO models manage to focus on the most important parts of the image?
I'm sorry, can you repeat the...
Yes, can you talk in the microphone? microphone. So if you have any insight on how do the self-supervised DINO models manage to focus on the most important parts of the image?
Okay. I think in the DINO algorithm, as I showed you, there are local crops and global crops. The global crops are almost the entire image. But this really depends on the training dataset. In the ImageNet dataset, there is a bias that actually there is always an object that is central to the image, like the Bornberger Tor. And when you do a global crops, that is almost the entire image, you always have part of this object, which means that there is it's really probable that you will have in the local crop some part of the global object. But if you use another dataset, probably you have to adjust the size of the crops.
Thank you. Now, a difficult question. How would you check the quality of your clustering if the number of classes is in the thousands with more than 100,000 images?
I think you can try to answer that. So it's very difficult. This is why we didn't do it for gold landmarks. I think what you can do is just select a subset of images, a subset of classes. Just if you did classification, you can check, for instance, the cluster that performed the worst or those that performed the best, compare them together, do like some confusion matrices, and check which clusters are mixing up from each other. So you cannot visualize them all together, but just visualize what you need to visualize.
Thank you. How hard is it to maintain a Milvus cluster in production? Do you need to be an expert in Kubernetes?
So as I said in the project where you use Milvus, yes, they kind of had to be an expert in Kubernetes. Because there are a lot of microservices, and I try to debug it myself. I'm not an expert, and I failed. And so yes, so they can. And even for expert in Kubernetes, there are a lot of microservices. Which it's hard to understand what they all do. There are a lot of logs to check. So now the bugs we faced are fixed, so it's not a problem anymore. But I would still recommend, if you don't have a production DevOps team, to use the managed version. So there is a service for Milvus where you can pay them to deploy it on either AWS or GCP.
That makes sense. Sometimes it's worth spending some money. Another question, could you manually mark regions to focus on in the query image and use the local features instead of those of the entire query image?
Yes, that's something we could do, and the easiest way to do this is to actually, if I wanted to do this myself, I would simply crop the input image. So probably the easiest way is to integrate this in the UI of your tool, like make it easy for the user to crop its input image.
Now, a special one. What GPU did you use to retrain DINO?
We did not retrain DINO. It's trained on, as we said, we're using pre-trained models. I think Antoine tried to retrain DINO, so you can talk about it.
See, we did it once with a very small GPU. I think it was a RTX 2080, and it took close to 100 days. So don't do that.
Did you run the demo here locally?
So the index of 762K images is quite big, so it was lagging on my computer. So I did not run it locally. We have a machine at Sikara where I just SSH to it. So all the computing of the representation, etc., is done on my computer, but just the Milvus engine is running in Paris.
Okay, one last quick question, most voted one. Do you plan to open source any parts of your implementation?
If you want to, we can, but we need to do some cleaning.
Thanks a lot for being here. It was really nice to have you.